let's explore JASP a little bit. So I am running JASP 0.14, which is the current build of just another statistics program, the friendly folks at jaspstats.org. If you want to take it for a spin, this is an R-based program that is supposed to model SPSS, which is owned by IBM. It's supposed to model it, the same kind of graphical user interface, point and click. But you can also, work with JASP to learn R, which is a statistical programming language. And it's a really simple program to use, in my opinion. And the creators of JASP out in the Netherlands, I believe, Western Europe, in that area, and some folks over here in the United States as well, developed this. It's an open source, completely free, and it's being, as they say, developed at a breakneck speed. Okay. It's still technically a preview beta build, and so they're still working on it. One of the things that I wanted to talk about for the remainder of this video is one of their additional modules that I came across. So one of the main things that these guys and gals do is they've really catered this particular product to not only frequentist scientists, so classical statisticians or classical researchers using classical statistical things like ANOVA and t-tests. They've really catered this program quite a bit to Bayesian scientists. So actually, before I click on that, I gotta open some data. So let's open this invisibility cloak data, and then we'll come back to something else. But I just wanted to show, like, if you go into t-test, you have it broken down. This is base program. So in the base program, you have Bayesian counterparts to the classical tests. Okay. And these are the base modules. But there's also one that I came across, Learn Bayes. So I know a little bit about Bayes, but I don't know a lot about Bayes. And I don't really know a ton about how to do Bayesian statistics. So let's learn Bayes with this one. Let's get the introductory text in here so we can learn how to do it. Okay, so let's successes and failures. Let's load that into outcome and see what happens. Correct is our successes and incorrect is our failures. Okay, the data selection allows you to specify data for output. Okay, loaded into JASP. In addition, variable levels need to be classified into successes and failures. So we have successes and failures. Success, I would imagine, is correct, and failures incorrect. Why not? And we can get this, or we cannot get that. Okay, well, it seems like it's a good idea. Successes were 70 out of 150, and failures were 80 out of 150. So that's their proportion there out of 100, or 1 in that case. So let's close up data and let's specify this model. The binomial estimation analysis offers two types of prior distributions for parameter theta that represent the underlying population proportion. And if that's not theta, my apologies to any Bayesian statistician here. Definitely not my intent to get any of that wrong. The binomial, okay, so spike for concentrating all mass probability at one point. This represents the prior belief that the population proportion is theta naught. With certainty, this conviction is so strong that no data can move this prior belief. Hence, the posterior is also a spike at 0, theta naught. The prior and posterior mean then corresponds to location at the spike. Beta, alpha beta, for allocating probability density across all values of the parameter theta according to the beta distribution of parameters alpha and beta. The prior mean can be computed as alpha divided by alpha plus beta. After observing S successes and F failures, the posterior distribution updates to beta, which is alpha plus successes, comma, beta plus failures, with a mean computed correspondingly. The estimation summary table displays numerical summaries for the individual models. The displayed point estimate can be changed using the point estimate option. The table is composed of the following columns, and we'll go through that in just a second. So we're going to just do model 1, and we're going to call it spike, and we're going to say that's 50%. Success and failure is 50-50. Let's do that. Okay, so here we have the model estimation. So the model is the model name. We just called it model 1. The specified prior distribution for parameter theta, we have a spike at 0.5. So 50-50, I would imagine. So that's the mean of the population proportion. Is we know that it was a coin flip, I guess. So the prior mean was 0.5. This is the mean of the specified prior distribution. And the posterior, which is what we're trying to estimate, the estimated posterior distribution for the parameter. Okay. The prior distribution updated with data. So the spike at 0.5 is what we plan to do. And the posterior mean, the mean of the posterior distribution, is also 0.5, which is successes that are 70% successes, or excuse me, not 70% successes, 70 successes and 80 failures. And we can see that we're sort of around that. So it makes a lot of sense that we would also see 0.5 as the posterior mean, which makes a lot of sense. I don't know if I'm doing this right, but that's what the Learn Bayes module is saying. Let's see if we can get some inference going. It's a bummer that Learn Bayes has stopped working. There we go. So here's the spike for model 1. Oh, I wanted to add model 2 as the beta, and A is 1, A is 1, alpha is 1, and beta is 1. Hey, contingency. How's it going? So we see that if we say everything is 1-to-1, that's default. The prior mean is 0.5. Well, beta becomes 71, and alpha becomes 71, and beta becomes 81, and so the prior mean is 0.56. And the model 2 is this horizontal line, and model 1 is this line. All posterior plots. So these are all prior plots, and these are the posterior plots. So model 2 is actually a little bit lower than model 1 with this spike here. So the prior distribution option displays the prior distribution plots for parameter theta. Spike prior distributions are visualized as arrows, signifying that their density is infinite. Okay. And beta distribute, and that would make sense because, you know, if you flip a coin an infinite amount of times, then I think it would just center itself on 0.5, right? So its density is infinite. That makes sense to me. And beta distributions are visualized as continuous lines. So here we have the horizontal. The all option shows you all prior distributions for parameter theta on top of each other, allowing for easier comparison with a common density and probability scale on the y-axis. I see. Density and probability. That's pretty cool. And so you could do stacked. I don't know. I don't have enough, I guess. So that's, this is model 2 stacked, and then we can do individual ones. I like all. All seems to be cleaner, I want to say. It seems to be cleaner. And then the posterior distributions are this one. And we have it as all as well. Posterior distribution option displays the posterior distribution plots for parameter theta. Spike prior distributions are visualized as arrows, signifying that their density is infinite, which would make sense. Again, same rationale, I would imagine, is similar here. And beta distributions are visualized as continuous lines. Yeah. The all option shows all posterior distributions on top of each other, allowing for easier comparison with the common density and probability scale on the y-axis. So we have a very thin, with this data, with these 150 responses, we have this data. And that's why it's pretty thin around what it was, 0.467. So 0.467, I guess, would say the probability of a success is actually a little bit lower than half and half, I guess. That's what I'm seeing there. So let's close inference and we'll leave those there. Sequential analysis is, I'm going to add the point estimate and the interval. We'll see what happens here. Point estimate and interval. Did anything load? So it's still working. Okay. Point estimates. The point estimate option displays a plot with the sequential updating of the point estimate theta on the y-axis. Okay. The figure visualizes the updating process as if the individual data points were arriving one after another on the x-axis. Okay. The all option shows either the mean or the median for all specified models in one figure, allowing for easier comparison. Okay, that's fair. It is possible to visualize different types of point estimates and credible intervals, which are CIs as well. Confidence intervals, credible intervals. Central is a central interval or quantile that covers the central mass percent area of the distribution. Okay, so it's mean, median, or mode, and then you can do a central with a mass of 95%. I would imagine that is very similar to doing a confidence interval at 95% confidence interval. I would imagine that would be the case. But that's pretty cool. It gives you uncertainty boxes for your beta distribution. Okay, so the beta distribution is kind of doing this. And you can see that it actually at one point does dip below this 0.5 line, and that's where that's interesting, actually. That's why it sort of converges at 0.467. It's a little bit lower than half and half. That's what I think. It's my educated guess at this point, looking at this. HPD, a highest... Okay, so you could change that to HPD. Highest posterior density interval that covers mass percent area with the shortest range. So we could change that to HPD, and then I'll change the plot here. It doesn't look any different to me, to be honest. And then custom is you can define a lower and upper bound. Okay. The updating table option generates a numerical summary of the displayed figures. Updating table. Ah, there it is. Huh. So model 1, if we just say spike at 0.5, it's what it's doing. Model 2, a beta distribution. You can see the change here as we go through all of the cases. That's rather cool. Sequential analysis. The interval option displays a sequential plot with the probability parameter theta lying inside of the interval ranging from lower to upper on the y-axis. Okay, so theta, the probability between 0.25 and 0.75. So after the, I don't know, 40th, 35th or so, up at least the 50th distribution, or observation, not distribution, looks like it, you know, that's where it converges in between this two. Figure visualizes the updating process of the individual data points we're arriving one after the other. So, of course, more observations means higher confidence, I guess, or credibility in your point estimate. The all option shows the probability of parameter theta lying inside the specified range for all models in one figure, allowing for easier comparison. Okay, I like that. The updating table option generates a numerical summary of the figures. Displayed figures, excuse me. Okay, so that's sequential analysis. Final piece here is we're gonna do 100 more future trials to predict how the point estimate works, I suppose. And I'm going to get a summary with the point estimate. It's gonna do 100 more future trials. So I'm assuming that means 100 more coin flips in the success failures thing, sort of idea. Okay, and it should load here. There we go. So before we look at what came out of that, the posterior prediction selection allows the prediction of future data based on the estimated models. When prior based predictions are desired, the data can be removed from the data section, the posterior, after seeing no data equals the prior. For a model with a spike prior distribution for parameter theta, predictions for n future observations follows a binomial distribution with size n and chance parameter theta not equal to the location of the prior distribution. The mean prediction can be computed as n times theta naught for a model with a beta prior distribution for parameter theta. The predictive distribution is the beta binomial distribution with size n and a posterior beta distribution parameters alpha and beta. The mean of predictions can be computed as n times alpha divided by alpha plus beta. Prediction summary table displays numerical summaries for that. So the model is the model. Posterior is the estimate from the previous data model modules up here. The posterior mean, the mean of the specified posterior distribution, prediction successes, the predictive distribution of the new data, and the prediction mean, the mean of the predicted data. Okay, so here we have posterior mean 0.5 and 0.46. Okay. And we are predicting that out of 100, 50 will be successes and 50 will be failures, which makes a lot of sense to a coin flip, if we have a sufficient sample size, I would imagine. But the beta binomial, doing the math here, 71, 81, and 0.467 with 100, we end up with only 46 successes, 46.7, which makes sense, right? Because we're multiplying by 100 from 46.7, moving the decimal place over by 2, right? So 46.7 is the predicted amount of successes, and it has a standard deviation. So there's variance there that could potentially be, but right, this is just a prediction. So it's a point estimate. That point estimate is surrounded by uncertainty. And we can get plots for that. And that's the last thing that I want to point out with this particular module. And yeah, and then we'll end there. So here we get the plot. The posterior predictive distribution option displays figures of predictive distributions based on posterior distributions of the individual models. The show sample proportions checkbox transform the figures with predicted data number of successes into figures with sample proportions. Okay, so there you go. Out of 100, the vast majority will be around 0.5. or 50 number of successes, where this is a smaller distribution with a slightly wider variance noted here of those 100 things. And so the distribution, so fewer people are going to, I guess this is 46 right here, fewer successes in the next 100 shots. That's quite interesting. I think I'm going to try to learn more about it. So let's look at the Bayesian, the Emily Rosa, excuse me. So this is this data set. So this is the binomial estimation. This is learn. And then this is just the Bayesian binomial test. So binomial estimation is not the same thing as learning how to do the binomial test. So you can do the binomial testing learn here, which I will do in a future video. And so this is the data. Emily Rosa provides correct and incorrect decisions from a therapeutic touch practitioners in Emily Rosa's famous experiment. In the initial trial, the subject stated the correct location of the investigator's hand in 70 of the 150 tries. And there you go. Our beta distribution estimated that 47%. So that's really cool. That's really cool. All right. That's the Learn Bayes module in JASP 0.14. Thanks for watching this video. If you have any comments, suggestions, or feedback, especially with a guy who doesn't understand Bayes fully yet, like I didn't learn Bayesian statistics in graduate school, you can drop some knowledge in the comment section below. Thanks for watching.